Hello. So, in this lecture, we are going to solve one more example on modal analysis. In the last lecture, we have used modal analysis or modal expansion theorem to solve a force vibration problem of a 3-degree of freedom system as an example. So, here we are going to adopt the same technique, but solve a problem on free vibration. So, this is the problem. So, we have a system whose mass matrix and the stiffness matrices are given. So, the natural frequencies and mode shapes we have figured out and we have given the solution, though it's very easy to find out this. We all know how to solve the natural frequencies and mode shape. Just to cut short the time, we have evaluated already and we have given the values. So, we need to find out the response of this system using generalized coordinate, that is using modal analysis for the initial conditions given. So, the initial conditions are the initial displacements are 0 for both the degrees of freedom and the initial velocity is non-zero V0 for the first degree of freedom and 0 for the second degree of freedom. So, let us see how we can solve this system. So, the first thing that we are going to do is we are going to find out. So, the mode shapes are given as R1, which is 1.00 and 1.366. So, this is the first mode shape and the second mode shape is given as 1.0 and minus 0.366. So, these are not mass normalized. So, let us first mass normalize this mode shape. So, mass normalization of mode shape. Okay. So, I have to evaluate this product R1 transpose into M into R1. Okay. So, this product is 1.000, 1.366 and then the mass matrix is M 0 0 to M and into 1. Okay. If I evaluate this, I have 1.000. So, if you evaluate this product, this is going to be 4.732 m. Therefore, R1 mass normalized is 1 by root over 4.732 m into 1.000 and 1.366. Similarly, the mass normalized second mode shape is 1 by 0.856 root over m 1.00. And if I evaluate this, this is 1 by 2.175 into root over m into 1.000 by 1.366. Okay. So, we have got the mass normalized mode shape. So, let us write down the mass normalized modal matrix. So, if I write down the mass normalized modal matrix is going to be R1 mass normalized and R2 mass normalized. This is going to be 1 by root over m, which is going to be 1 by root over m into okay. So, if I do again the transformation, that is u, my physical coordinate is phi, the modal matrix, into the natural coordinate or the generalized coordinate, and substitute this into the equation of motion, which is m into u double dot plus k into u is equal to 0. If I substitute this here, I can directly say that the equations that I am going to get is n1 eta 1 double dot t plus omega 1 square eta 1 t is equal to 0. Since this is a free vibration problem, eta 2 double dot t plus omega 2 square eta 2 t is equal to 0. So, now what I need to do is I need to solve these two equations to get eta 1 t and eta 2 t. So, we have seen similar equations before and we know how to solve this. So, the solution of this two equation is eta 1 t is nothing but eta 1 0 cos omega 1 t plus eta 1 dot 0 by omega 1 sin omega 1 t, and eta 2 t is eta 2 0 into cos omega 1 t plus eta 2 dot 0 by omega 2 sin of omega 2 t. So, now what I need the values of eta 1 0, I need the values of eta 1 dot 0, eta 2 0 and eta 2 dot 0. So, if I know this, I can always say find out eta 1 and eta 2 t. So, these are nothing but the free vibration solutions. So, this is very similar to my one single degree of freedom system, which is u double dot t plus omega square u t is equal to 0. This we have dealt a lot in the earlier lectures on single degree of freedom system. Now, our job is to find out the initial conditions on etas. We have the initial conditions on the displacements u and the velocities u dot. We now need to find eta in terms of those. So, how would we do that? So, we have this relation that u is phi into eta. So, I can say that u 1 0, u 2 0 is phi, I know phi, and eta 1 0, eta 2 0. Similarly, I can say u 1 dot 0, u 2 dot 0 is phi into eta 1 dot 0, eta 2 dot 0. Okay. Now, the first thing that comes into mind, so this I know, this I need to know. So, the first thing that comes into mind is that why do not I find out eta 1 0, eta 2 0 as phi inverse u 1 0 into u 2 0, and similarly I can find out the initial velocity eta 1 0 and eta 1 dot 0 and eta 2 dot 0 as phi inverse right. So, this is known. So, I know also phi, I can take the inverse and multiply with this and get this. This is correct, this is not a wrong method, but this is not the easiest method or the recommended method. This is actually not recommended. So, let us, because it is not recommended, because finding out phi inverse, you need to do it numerically. It is not very easy to find out the inverse of a 3 by 3 matrix, for 2 by 2 matrix, or for that matter 3 by 3 or even larger matrix. So, it is always difficult to find out the inverse. You have to use use a numerical technique to find that out. So, instead of that, we can actually find it out in a much easier way. So, what I am going to do is I am going to take this two equation, multiply each side by m first, and then again multiply by phi transpose. Right. So, similarly here I will multiply by m and I will multiply by phi transpose, and I will multiply both sides. So, phi transpose into m. Now, this product is nothing but an identity matrix if we have the mass normalized mode shapes. So, this is also an identity matrix. So, this side is gone. So, therefore, I will be left with phi transpose m into u 1 0 u 2 0 is equal to eta 1 0 and eta 2 0. Similarly, I can say phi transpose into m into u 1 dot 0 u 2 dot 0, and that is equal to eta 1 dot 0 and eta 2 dot 0. So, this is just simple multiplication of two matrices which can be easily found out in contrast to the inverse of a matrix. So, I know this, I can easily find out this product, and therefore, I can know the initial conditions on eta. So, let us do that for this particular problem, and then I can say eta 1 0 eta 2 0 is phi transpose into m. Now, u 1 0 and u 2 0 are zeros. So, this is of course eta 1 0 and eta 2 0 are going to be 0, and similarly eta 1 dot 0 and eta 2 dot 0 is going to be the transpose of phi matrix, which is 1.0 by 2.175 and then 1.366 by 2.175, 1 by 0.875 and minus into the mass matrix, which is m 0 0 2 m into my initial velocities on u's. So, which is v0 and 0. So, if I try to evaluate this, this is 1 by root over m into this matrix into I am going to have a vector which is m v0 and 0. So, if I find that out, it is going to be 1 by root over m, and then I will have m v0 by 2.175 and then m v0 by 0.875. So, these are the values of eta 10 and eta 20. Okay. So, now what I have got the initial conditions on etas. Now, I can go back to the solution where eta 1 t is eta 1 0 cos omega 1 t plus eta 1 dot 0 by omega 1 into sin omega 1 t. So, out of that this is equal to 0 and this is going to give me m v 0 by 0.875 root over m by omega 1 into sin omega 1 t. So, that is equal to that is equal to v 0 into root over m by 0.875 to omega 1 sin omega 1 t. Similarly, eta 2 t is going to be v 0 by root over m into this should have been this should have been 0.2175. So, this is 0.875 omega 2 sin omega 2 t. So, I have got the solution for eta 1 and eta 2. So, my u1 u2 t is nothing but my phi matrix, which is 1.0 by 2.175 root over m and then 1.366 by 2.175 into root over m, then 1.0 by 0.875 root over m and minus 0.366 by 0.875 root over m, and that I have to multiply with v 0 root over m by 2.175 by omega 1 sin omega 1 t and then v 0 by root over m into 0.875 omega 2 by sin omega 2 t. Right. So, if this is written in an expanded form, what am I going to get? I am going to get u1 t as v 0 by 2.175 whole square omega 1 sin omega 1 t plus v 0 into 0.875 square omega 2 into sin omega 2 t. Similarly, u2 t is going to be V 0 1.366 by 2.175 whole square omega 1 sin omega 1 t plus minus 0.366 V 0 by 0.875 whole square omega 2 by sin omega 2 t. So, this is going to be the final solution for the system. So, this is the free vibration response of the 2 degree of freedom system using for the initial conditions given. So, we could have solved this problem in a similar way that we did earlier for a free vibration case by taking the linear combination of the normal modes of vibration under free vibration condition, and we can also solve in this way and the two results should match. But this method of solution gives a much more generalized method of solution, and this can be applied by writing a small analytical code to find out a numerical code to find out the mode shapes, the mass normalized mode shape, and that would actually help us to get a much easier solution of this system. Now, let us look into the solution from a physical aspect. So, we see that the free vibration response for both the degrees of freedom contains the first natural frequency as well as the second natural frequency. So, it is a combination of two sinusoids having the two natural frequencies. So, it can be summarized that if we consider the free vibration problem of a multi-degree of freedom system, then each of the degrees of freedom of this multi-degree of freedom system is going to vibrate as a combination of the several sinusoid function of, and each sinusoid having the one of the natural frequencies of the system. So, if we have a n degree of freedom system, the free vibration response of any one degree of freedom of this n degree of freedom system is going to be a linear combination of n sinusoids having the n natural frequencies, right. So, this is a 2 degree of freedom, omega 1 and omega 2 are the two natural frequency. So, the response is a combination of sin omega 1 t and sin omega 2 t. Similarly, u 2 is also a combination of sin omega 1 t and sin omega 2 t. So, all the frequencies are going to natural frequencies are going to be seen in the free vibration response of a multi-degree of freedom system. With this, we will complete this lecture on modal analysis. In the next lecture, we will talk about rigid body modes and how to model damping in a multi-degree of freedom system. Thank you.